You've created a fantastic machine learning model and you want to be able to share this with others. What are your options? Well, the first thing you can do is export your model, package it up some way, send it to another computer, and then somebody else can run that model and make predictions. Another way is to create a Docker container or some type of package that can be deployed for a web solution on the cloud. So a couple examples of those are like with Google Cloud, Amazon, or also Azure with Microsoft, and be able to deploy that in a distributed way so it scales up with many users, maybe through a mobile platform, an app, or other type of application where you deploy that. Another option is for embedded systems where you might want to export code that can run on these embedded devices. So you're going to be running on this specialized architecture that might be running on a drone or UAV, or you might send that update to an automobile that will have a new autopilot or other type of feature that you can push out to these embedded devices. We're going to go through some of the strategies to do that, how to take your model, package it up, and then send it somewhere else to be able to run on a different computer system and produce predictions. So let's get into some of the example code here. There's some excellent examples here, even with the Tesla autopilot, you have a number of chips and custom computing platforms that they've created both on the automobile, but also for training the machine learning for autopilot. And you can see some examples here of what they're doing. I also encourage you to go to this Tesla AI Day. Shows some of the process of deploying these machine learning models in production environments, like on a vehicle or with the Tesla robot. So that's definitely worth a look. There's some highlight videos out there as well if you want to just get to some of the main points. All right, so let's go to this deploy machine learning notebook. And you can either run this through Jupyter Colab or Jupyter Notebook in Google Colab, or come here and go ahead and download it to your computer. Just select right click, save link as, and then you can save the IPython notebook. So I have that opened already here. I'm going to go through some of these exercises. The first one is just using pickle files. And pickle files are one way to encapsulate Python objects, lists, or anything else that's accessible in a Python session. Now, there are some exceptions to this. For example, some of the machine learning models, you can't include those in a pickle file, so we'll use an H5 or HDF5 file that we can then deploy somewhere else. But let's start with pickle files. These are relatively easy, and you can encapsulate things in them, any Python list of objects. So I'm just going to create a list, 1, 2, and 3. I'll import the pickle package and then dump that the contents of Z into this pickle file. I'll open it and call the file z.pkl. And then you can also see here a WB. I'm going to write it in binary form. And so it's going to be computer readable form. It's not, you can't open it with a text file and be able to decipher what's in there. Okay, so when I run this, and I'm also going to, let me just go ahead and put this here so I can see my desktop. As I run it, I'm going to see this pickle file created. And if I open it up with something like a notepad editor, I can see that it's in binary form. I can't necessarily read it myself. All right, but let's go ahead and read it with Python. We're going to, if we had another computer, we could send that z.pkl file over, import pickle, and then load it. And then I'm going to create this new y variable right here and print out y. And I can see it just says 1, 2, and 3. But I could do other things in here as well. Let's say I had a string. Let's say a message was hello. All right, and then I wanted to include this in the contents that I dump over into the pickle file. And then when I read this, it's going to include these two things. So maybe I want to say that's y and n, and then I can print those separately. Okay, so I can unpack them. If I know how many elements there are, then I can unpack them this way. If I don't, then I can just say, let me go ahead and read that out as the value q, for example, and then read them in. Okay, so that's an example of packaging with pickle, and then unpackaging and loading that pickle file. Again, this is going to be a read binary. Now, the other way to do this is with HDF5 models. We have some Python objects, such as Keras models or TensorFlow models, can't be stored as pickle files. So the hierarchical data format, version 5, there may be future versions of this, it's a file format that's designed to store large amounts of data, model architectures, parameter weights, or other information. So let's to do this, you can use the Keras, you can save it, okay, model.save, and then you can create the file name like store.h5. Now you can restore that and load it back in with this Keras models load model, and then you can retrieve it back. Now let's go ahead and do that just for an image classification. This is another example in the course, but I'm going to go ahead and just import some of these packages, and then let's go ahead and just download the TensorFlow model that I have trained. Now chances are, if you use this one, it's a different version of TensorFlow. It may have some warnings when you unpackage it. It says, hey, this new option was not in here, or it might be even incompatible. So if you want to regenerate this file, you can do that. Just come back to the course website. You can come down here to the bit classification, and at the very bottom, you can see a notebook for training this crack classification. So you can generate your own H5 file if this one doesn't work and be able to use it in this example. But just go ahead and try this first. It's going to get it from the URL. It's going to retrieve it, okay, download the file. And then I'm also going to get concrete cracks. These are going to be some image files. So if I run this, I'm going to see that it's going to download those files. This one's about 2.4 megabytes. That one is also, let's see how much is that one. I'm going to get properties. That's about 7 megabytes. The cracks, okay, you can see it's 2.7 megabytes. And again, if I open this up with a Notepad++ editor or text editor, you can see it's in binary format. It has some text values in there, but largely it's unreadable. So it stores all of the parameter weights and the model architecture in this binary format. Now you can see here in concrete cracks that I'm going to have train and test folders. These are positive or negative for these concrete cracks. And what I want to do is just extract those, unzip them. So let's go ahead and just unzip. We're going to use a zip file, and we'll extract all, and then we'll remove the original file. Okay, so if I run this again, you'll see that it replaces that zipped archive with the unzipped archive here, and has removed that original zip file. All right, now I'm just going to import those. This is not the subject of this tutorial here. If you want more, go back to that other page. And you can see here's the important part right here, where I've loaded in the Keras model, or the TensorFlow model. And you can see that's the cracks.h5 file. So that's all I needed to do. It was trained somewhere else, and I'm just loading it into this session. And then I can use the predictions to determine whether there are cracks. Okay, I'm going to have negative and positive. I'll make a prediction. And all right, and then just say whether it was successful or not in predicting it. And I'll generate a random value from there and show the prediction. So here it is. Here's the first image. Found 200 images belonging to two classes, or that's positive crack or negative crack. And this image was negative for predicted, and it was the true label was also negative, so it was correct. Now, if I wanted to just break this out even further, I could just take this load, load the model once and then randomly make predictions. So even if I wanted to create a new cell below, I wouldn't have to re-download all the images every time I wanted to make a prediction. So it's just going to load the model, make a prediction, and you can see that it's doing a fairly good job with, it's about 95% accurate based on the statistics that we saw from the training. So you can see, you can take a picture with concrete and determine if there's a crack in it. Maybe that's something that you deploy to a web app where the camera from the cell phone or the computer takes an image and then determines if a crack is there or not. Okay, so that's an example of deploying a machine learning model. Okay, so let's go ahead and also do other types as well. So that was Keras, TensorFlow. But let's say you have something in Scikit-learn and you can pickle it up. So here's make blobs. This is our standard make blobs to just create this data set. We're going to split it into 80% and 20% for training and testing respectively. We'll train it and fit with logistic regression in this case, and then import the pickle file and then store. This is our logistic regression model, and then I also have some of my test data. All right, and then I'm going to dump all of that to store.pkl. And then let's go ahead and just view the data just so we can see what we had created. Okay, so when I run it, you can see this store.pkl that was just created right there. Very small. This was 4.6 kilobytes. So logistic regression models are very memory efficient, as opposed to this one, 4.7 megabytes for the image classification. So it depends on the application, how much memory, how much time it's going to take to load and store that. But some like logistic regression are going to be very small. All right, so here's our data that we're trying to classify. Now let's go ahead and unpickle that and make a prediction. So I'm going to retrieve the model and the test data, and then I'll make a prediction and then show a confusion matrix on the values that were part of my test set. All right, so it did a very good job. Here you can see 99 values were classified correctly, 1 incorrect, where it said it was predicted a 1, but it was actually a 0. And then the other one had a 100% success rate on the prediction. True values of 1, 100% of them were also classified as 1. So the main thing here is that we're loading the pickle file and then making a prediction. All right, let's do the same thing, but for number identification. We're going to, this is just an example of how to do this with a neural network, and then we're going to do it with k nearest neighbors as well, and then deploy that. Okay, so here's a multi-layer perceptron classifier, neural network. From Scikit-learn, there's just some options. And again, this is not the focus of this tutorial, so I'm going to go through this pretty quickly. We're just going to load the data set, these types of numbers, split it into test and train subsets, 50% each. We'll fit our classifier, in this case, the neural network, and then we'll test on the second half of the data and then show the number. Okay, so this is something that you can run locally on a computer, but now if we wanted to train it and then deploy that model for optical character recognition, for example, then we could do that. Okay, so here's the model and test data. We're going to just do this with k nearest neighbors now. Load some packages. Okay, and we're going to take 5 nearest neighbors and then load the digits data set. We'll split into the train and test sets, 50% each. And then we'll learn the digits, train the k nearest neighbors, okay? And then import pickle and create store.pkl. All right, so when I run this, okay, it's going to just update this pkl file. Here it's about 2 megabytes. So k nearest neighbors, they can be a much more for storage because you're basically storing the data from the training set to then make the predictions. It needs to know how many nearest neighbors there were there. So this is a factor. You need to check how much is being stored there. And then let's go ahead and deploy this. Okay, so we're going to retrieve the model and the data. And here's our loading. Okay, we stored the classifier and then the digits. Here's our loading. And it might be interesting. Let me go ahead and just do this only for the classifier itself. Okay, so that's going to be pickle dump. And then if I only have the classifier, and I'll open a new pickle file, and I'll write in binary format. Okay, so let's go and just get the, and you can see it's about 450 kilobytes. So a little bit less just for the classifier itself. The additional maybe 2 megabytes or almost 2 megabytes was for the images. Okay, the digits right there. Okay, so now let's go ahead and just, after we've loaded this, okay, we'll test on the second to last number. All right, so when we run that, we can see this was a 9. Let's go on the third to last number. Okay, and there's a predicted 8. And so you can change these numbers here just to show it and what the predicted value is. All right, so there are other types of models that we can also package up. This is an example of a model predictive controller, and this is with Gecko package in Python. The first time through, the application's created and stored as this m.pkl file. And when the m.pkl file exists, the pickle file is reloaded instead of creating a new application. So this is important for things like real-time control, where if the computer is rebooted, when it comes back up, you want it to remember the instance that was created and be able to redo the calculations. So this is another way of deploying, is that we can see if the file exists, then unpickle the application. So this is an example with Gecko. If it exists, then I'm just going to load the model from the previous call and then solve it. Okay, make the prediction on what the next move plan should be. And if not, then I'll define the model and create it again. So here is an example with Gecko. We have MVP. The manipulated variable is P. The controlled variable, thing that I'm trying to drive to a target, is V. And then we have an equation, and then option is model predictive control. And we have our status 1 and dcost, okay? And then some other options that we need as well. And there I'm going to solve it. And then every time through, whether it created it for the first time or it loaded it, I'm going to go ahead and dump that back out into m.pkl file. And then I'll generate a figure with the predictions. So when I run this the first time, you can see that it starts at a value of 0. And then when I run it the next time, you can see that it's going to start at the next time step. So it time shifted it over, it's still trying to drive it up to a set point of 10. And then if I do this again, multiple times, running through it, you can see that it's progressing up there. So it's like it knows that there's a time dependence of this. It reloads it and doesn't start again from 0, but it starts from the next time point, as if the controller were cycling every second, and then this became the new starting point for the prediction. Okay, so that's it on this tutorial. There's all of the source code here, and I'll include a link to it if you'd like to go through this and the examples on how to deploy these machine learned models for classification or regression. It showed a couple examples with image classification or just these simple data sets, and how to encapsulate this so you can transfer it to another computer. I will say there's another way of doing this that is particularly good because it allows you to get all the dependencies and send it out and deploy it as a container. And one of these is a Docker container that can also be deployed to cloud services such as Google Cloud, Azure Container Instances, or Amazon Elastic Container Service. So I encourage you to take a look at this as well. Here's a very nice overview and tutorial to create a Python image, to create a Python application, for example. But there are other types of applications or computing environments that you can create and then deploy. So you'll build the images, and there are just specific instructions here on how to do that. So I encourage you to take a look at this just to see how to build these images and then run the containers. There's very little overhead with these. Some of the testing that was shown, it's fractions of a percent of overhead to run this container, this application in a container versus run it natively. So I encourage you to take a look at it. You can deploy it to things like Google Cloud and deploy this container on a compute engine. You can also do this with Azure Container Instances, and they're very good tutorials to help you get started. And then a final one here, Amazon Elastic Container Service. So all of those are available. One of the advantages of this is it helps you scale up. So if you have an application where there's going to have some use during certain times of the day, but other times not, or you're developing software that, a compute service or a prediction, some type of thing that you want to get out to others, and that might scale rapidly, then cloud computing is nice because it will scale with your audience. And so you don't necessarily need to worry about the physical hardware. You can focus on creating the container, deploying it, and then scaling up with the use of those who use your predictions from your machine learning. Okay, well, I hope you've enjoyed this tutorial. I'm glad that you're following along with this Machine Learning for Engineers course. I have more content coming up, and so I encourage you to take a look and provide any suggestions on other things that you'd like to see in this course. So thanks for joining.